So today we're going to look at assessing ventilation, and then we'll move on to gas diffusion, and we will end with transport of oxygen and carbon dioxide and kind of how it relates to gas diffusion. We'll save disease processes for Monday. So where we left off was looking at the processes of inspiration, bringing air in, expiration, breathing air out, and how that was affected by changing the volume of the thoracic cavity. That changed the pressure gradient, and air, really anything that follows simple diffusion has to go down the diffusion gradient from high concentration to low concentration, or in this case, high pressure to low pressure. And we're going to build upon that when we get to the law of partial pressures. Before we get to the law of partial pressures, we'll talk about assessing ventilation. This will be heavily redundant with lab, but getting it twice is better than not getting it at all. Respiratory volumes, and more specifically, respiratory capacities, which are when you add volumes together, can be used to assess respiratory status. Respiratory volumes and capacities can be indicative of a pulmonary disorder, whether it is obstructive or restrictive. These are the 4 volumes that you need to know what they are and be able to identify them from a graph. Tidal volume is the amount of air moved in and out of the lung with a normal breath. So normally we inspire about 500 mils of air. We're just at rest. It's hard to breathe. Like think about breathing and then not breathe deeply. I think doctors have conditioned us. But a normal breath in is about 500 mils of air. Normal breath out is about 500 mils of air. And this is actually only about 350 mils of fresh air when we inspire it, because it's going to mix with air that's already still in our conducting zones to make up that tidal volume. We'll talk about dead space in just a little bit. So tidal volume, a normal inspiration or normal exhalation, same amount of air is moved both directions. Inspiratory reserve volume is when we want to forcibly increase the tidal volume. So we want to breathe in as deep as we can. We take a giant breath in, and that will move about 2 to 3 liters of air. So we can take a deep breath in, and that moves a large amount of air. When we want to, if we need to, we'll talk about acid-base balance in a lot more detail. Breathing in deeply will affect those partial pressures a little bit. Anyway, okay, so volumes. Normal breath in, deep breath in, lots of air, 2 to 3 liters. So lots of air flooding the lungs. Then we will passively exhale that out. Expiratory reserve volume is the amount of air that can be forcibly expelled from the lungs. So after a normal exhale, and it's a much lower volume. We don't have as great of a capacity to compress that thoracic cavity beyond normal. Residual volume is the amount of air that always remains in the lungs. It's needed to keep alveoli open, and it gets trapped in other passages. But this is, you can't measure because you can't exhale that amount of air. So this is the amount that is going to just stay in the lungs to keep it open. There are 4 capacities that are listed, the 2 that you need to know. So capacities are the sum of 2 or more of those previous 4 volumes. And the 2 that are important to be able to calculate would be vital capacity. This is the total amount of exchangeable air. It's the sum of tidal volume plus inspiratory reserve volume plus expiratory reserve volume. So vital capacity is if you took a giant breath in and then you breathe all of it out. And if you're trying to do it as quick as possible, that's called forced vital capacity. And forced vital capacity is often used as an indicator of pulmonary disease by doing it for a certain amount of time. Total lung capacity, you can calculate it two ways, as tidal volume plus inspiratory reserve plus expiratory reserve plus residual volume, or it would be the same number if you did vital capacity plus the residual volume. Residual volume is about 1,200 mLs in men, a little less in women. So vital capacity plus, we normally give you the residual volume. There is anatomical dead space that still has air in it. We don't compress our bronchioles completely down to get rid of all the air. We leave some in there. So anatomical dead space is the air that remains in the passageways and does not contribute to gas exchange. It's about 150 mils out of our 500 mils of tidal volume. Alveolar dead space is going to affect why we don't have like 100% saturation. We've got a little bit of disconnect between ventilation and perfusion. And this is because not all of our alveoli are always available for gas exchange. Most of them are, but sometimes they're non-functional because we have a respiratory issue where we're getting lots of mucus production. Maybe there's pneumonia, maybe there's collapse, maybe there is damage due to like smoking or asbestos, but these can be non-functional, and that's called alveolar dead space. Total dead space, sum of anatomical and alveolar. The one that's probably more of interest is the anatomical dead space, just because it does affect tidal volume, meaning that we don't, even though we exchange 500 mils of air, it's not like it's all fresh air. This is a spirographic recording. So most of you don't have the e-text, but in the e-text is a funny video of how spirometry measurements used to be done. And they had these large water-filled chambers, and you put kind of like this mask on. It was very weird, very uncomfortable, and it made these drawings around this drum of paper. Kind of weird. Now it is so much easier. It's just an electronic breathing device in the computer. Makes a spirogram, and then of course, like computers do, they will calculate the respiratory rate, tidal volume, all four volumes, all four capacities, and it's just right there as a nice little readout. But you should know what each of the volumes are, what they measure, so that you have an appreciation for what these measurements are. The graphs usually are going to start around 1,000, but don't necessarily go off the graph. Usually we'll go and we'll give you a residual volume number because that might not be completely accurate. Okay. Then in the middle, this line, small sinusoidal curve, is tidal volume. In most of the graph paper, each of these between, so like 1,000, 2,000, 3,000, 4,000 are labeled. And then in most of the graph paper, that our spirograms are done on, have 4 boxes. So each one is 250 mils of air. So if this had a little dash in the middle at 2,500, to 3,000. That difference is 500 mils. So we move 500 mils in, move 500 mils out. Then take a deep breath. That starts here. It's the dark blue. Deep breath in, and that will be between 2 and 3 liters of air. So large volume. Then we'll passively exhale that. And then if we want to force additional air out, that's expiratory reserve. It's around 1,000, 1,200. And then we go back up to tidal volume. So if you see a graph similar to this, you should be able to identify tidal volume, inspiratory reserve volume, expiratory reserve volume. And then if you add those three together, you get the vital capacity. If you add these three plus residual volume, you calculate total lung capacity. So be able to identify the parts of the curve as well as write or determine what each of the volumes are. Again, you can't determine residual volume, as well as calculating vital capacity and calculating total lung capacity. You'll probably see these questions twice, both on a lab exam or a lab quiz, as well as the lecture exam. These have the average values for men and for women. Women tend to be, they're highly dependent on body size. So if you had a tall female, she would have larger lung volumes. And if you had a small male, it'd be closer to the female values. It's really more of a size, not a gender discrepancy. So spirometry is the old school method, and now it's electronic, can distinguish between obstructive pulmonary disease versus restrictive disease. Obstructive disease is when we have increased resistance, such as bronchitis. Restrictive is when we have reduced total lung capacity due to exposure to chemicals, tuberculosis, asbestos, fibrosis. In obstructive pulmonary disease, the volumes may increase due to hyperinflation. Restrictive disease is, by definition, reduced total lung capacity. For this slide, you should be able to identify that obstructive pulmonary disease is due to increased airway resistance, and restrictive disease is defined as a reduced total lung capacity. We've talked about volumes, which are measured, except for residual volume, which is estimated. Capacities, where we add volumes together. And then an additional pulmonary function test are rate tests. So remember, rates are there's a volume per unit of time. So sometimes it's liters per minute, sometimes it's mils per minute. At rest, normal minute ventilation, so the total amount of gas that flows in or out, is about 6 liters per minute. And you'll take the number, let's say this is a, let's do one more. Whoops, sorry. Say this is a 30-second strip. You would count the number of peaks, 1, 2, 3, 4, 5, 6. And then you'll need to multiply that by 2 because this represents 30 seconds. Minute ventilation is per minute. So you need to convert a 30-second strip to a 60-second strip. You'll get 12 respirations per minute times if you use the preceding graph, a tidal volume of 500 mils per minute. And then that would get you your 6 liters or 6,000 mils per minute. These values forced are also per time. So forced vital capacity is the amount of gas forcibly exhaled after taking a deep breath. And usually that is timed, how long that takes to complete getting all of the air out. Forced expiratory volume is the amount that is expelled usually in the first second. And again, these are diagnostic tests. So a forced test is a capacity per unit time, and it's used to examine lung function. Minute ventilation is something we monitor all the time. We are transitioning a little bit towards gas exchange. We're getting there. So alveolar ventilation rate is the flow of gases in and out of the alveoli during a particular time. It is a better indicator of effective ventilation. What this chart is trying to show is that ventilation, so you could increase the amount of air going in and out of your lungs in different ways. You can do slow, deep breathing, and normal breathing, and rapid, shallow breathing. And they would all have the same minute ventilation rate. In rapid and shallow, the tidal volume is less, but the respiratory rate is highest. Slow, deep breathing, so you're taking in more air, greater inspiratory reserve, and then letting it come out. You're going to increase, and it's not like a full capacity, this is just slow and deep. You increase tidal volume, lower your respiratory rate. This is where that dead space comes into effect, because rapid and shallow breathing, out of this 250, you still have 150 mils of dead air. So your fresh air is really only 100 mils. With slow and deep, you are bringing in 850 fresh mils of air per breath, and then normal is 350. So if you look at the amount of fresh air that is brought in times the respiratory rate, that gives you the alveolar ventilation rate. So fresh air times the respiratory rate gives the alveolar ventilation rate. And even though all three of these patterns produce the same amount of air going in and out over a minute, the amount of fresh, clean air is higher in slow, deep breathing, so that the alveoli have better ventilation. Okay, so slow, deep breathing provides the largest amount of alveolar ventilation rate. So how much fresh air is getting pushed into the alveoli per minute. Now, so we're transitioning to gas exchange. Gas exchange occurs between the lungs and the blood, as well as the blood and the tissue. External respiration is going to be diffusion of gases between the blood and at the lungs, because we're exchanging with external environmental air. Internal respiration, everything is internalized. This is between the blood and the tissues. Dependent on Dalton's law of partial pressures and Henry's law. We are going to have a lot of laws with gases because they fall under many like areas of physics, and so there are just lots of laws. So we started off last week with Boyle's law. And Boyle said P1 V1 equals P2 V2, which means translates into as pressure, well, let's do volume. As volume increases, so as we breathe in, we make a larger thoracic cavity. As volume increases, pressure decreases. So we open up that thoracic cavity, volume increases, the pressure decreases, air goes from high pressure to low pressure, so from out in the atmosphere and into the lungs. Then we are going to our next law. Our next law is Dalton. In Dalton, he has what's called a law of partial pressure. Law of partial pressure. And then we'll end up with Henry. In just a minute. So Dalton's law of partial pressure says that total pressure exerted by a mix of gases is equal to the sum of pressures exerted by each gas. We'll come back up to Henry. So at last lecture, we talked about how total atmospheric pressure equals 760 millimeters of mercury. We are concerned with the partial pressure of oxygen and the partial pressure of carbon dioxide, because we need oxygen to move and we need carbon dioxide to move, and gases will only move along their partial pressure gradient, and they'll move because it's diffusion from an area of high pressure to an area of low pressure. So we're going to create a high level of partial pressure in of oxygen in the alveoli through inspiration. That fresh air gives it a high concentration, partial pressure of oxygen. Then at the lungs, it comes into at that respiratory membrane on the other side, the partial pressure of oxygen, because we're pulmonary capillaries, these are going to be deoxygenated blood. The partial pressure of oxygen is going to be much lower, and so oxygen will move from the alveoli to the red blood cell. And the reverse happens for carbon dioxide. In order to calculate partial pressure, you need to know the atmospheric pressure, 760 millimeters of mercury, and then what percentage is present in the air or in the alveoli or in the capillary, whatever where you're measuring it. In atmospheric air at sea level, oxygen makes up 21% of the air. So the partial pressure of oxygen, and I never go out to 0.209, I just do it as 0.21 times 760. And I think I end up with 160 if I'm correct. Anyway. So take the percentage. This is in order to find the value of 760, move the decimal point over 2. And so it's 0.21 times 760 equals 160. About a fifth of the atmospheric pressure is attributed to oxygen, about 21%. This chart here does all of that calculating for you. So in atmospheric air at sea level that we breathe in, the ones we're concerned with are oxygen and carbon dioxide. Oxygen contributes 159 to that 760, carbon dioxide 0.3. The percentage of carbon dioxide in the air is very, very low. At the level of the alveoli, these percentages change a little bit. Nitrogen still is the greatest contributor, but the amount of water has gone up because we humidify air. That water contribution increases. In addition, the contribution of carbon dioxide increases because our body produces a lot of carbon dioxide and uses a lot of oxygen, so its contribution goes down. So again, these don't match atmospheric because of that intermixing of dead space gases with incoming gases, as well as we have a lot of carbon dioxide getting dropped off and oxygen leaving. So all of those processes together creates this change in percentages as well as partial pressure. We are going to be looking at the movement of oxygen and carbon dioxide from the alveoli with the blood. And that's the gradient that we are concerned with. So on the alveolar side, the gradients are 104 millimeters of mercury for oxygen and 40 for carbon dioxide. So these are the partial pressures in the alveolus. Do we want to, oxygen is going which direction? From the alveolus to the blood or the blood to the alveolus? Oxygen needs to get where eventually?
To the blood.
Right. So because eventually it's going to get to the tissue, so it needs to travel to the blood first. Okay. So is the partial pressure in the blood, is it going to be higher or lower than in the alveolus?
Lower.
Lower. So we know it needs to be less than 104, or else we wouldn't have movement of oxygen into the blood because we go from high to low. Now, what direction does carbon dioxide go?
The opposite.
Very good. So we need to move carbon dioxide from the blood into the alveoli so it can be expelled. Do we need a value of partial pressure that is higher or lower? And so is this value in the blood, is it higher or lower than in the alveolus?
Higher.
Higher. So we need to be over 40 because we have to move from high to low. This is an important concept to understand, that we're always going from high to low this is for oxygen, and then it'll be high to low for CO2, but we're always going from higher to lower. Henry's law is going to state that for gas mixtures in contact with liquids, which the blood is a liquid, each gas will dissolve in proportion to its partial pressure, but the amount of gas that dissolved depends on solubility and temperature. Temperature fluctuates. This becomes a little bit more of a factor when we get to tissues because our tissues generate a lot of heat. But at the level of the lung, this is your driver here. Okay, solubility. So gas dissolving into liquid like blood, dependent on partial pressure and solubility. Ooh. For solubility, carbon dioxide is 20 times more soluble in water than in oxygen. So if, well, we'll get, okay, so this is going to become important, and because in the blood, the partial pressure of carbon dioxide is only 45. And in the alveoli, it's only 40. That's really not much of a gradient. There's not much of a push from the partial pressure. So, but carbon dioxide diffuses just fine because it is so much more soluble. So for both oxygen and carbon dioxide, you'll need to understand which factor is more important. Is it the partial pressure difference or is it the solubility difference? Atmospheric gases, mainly nitrogen and oxygen, very little carbon dioxide and water vapor. But alveolar gas contains much more carbon dioxide and water vapor because we humidify it, gas exchange at the lungs, O2 is decreasing, carbon dioxide is increasing, and the mixing of alveolar gases. So we've got new air and old air mixing. So this is a good slide. For external respiration, so looking at the exchange of atmospheric air that's made its way to the alveoli, so the exchange of between the alveoli and the blood, which occurs at this respiratory membrane, it is going to primarily be under, like, its primary influence is partial pressure gradients and gas solubilities. For oxygen, it's really going to be this partial pressure gradient. For carbon dioxide, solubility is going to help its diffusion a lot. The thickness and surface area of the respiratory membrane, these normally don't limit it. The thickness is very, very thin, so that's not a barrier to diffusion. And the surface area of the alveoli and the respiratory membrane is tremendous. So these are not limiters unless there is a disease process. Surface area can be destroyed with something like emphysema because the alveoli, you lose alveoli and you keep the sac though. But the volume of respiratory membrane would go down. Thickness isn't usually, I guess there's probably a disease process associated with it as well. Ventilation perfusion coupling. So we have an alveolus, and it is getting an exchange of oxygen and carbon dioxide due to ventilation. Perfusion is how fast are the blood cells in the blood passing by this respiratory membrane. So if you were breathing slowly, like just even slow and deep, and then you were also exercising and making the blood go by really, really fast, that would decouple the system. It's not optimal. Normally, if you increase perfusion, you increase that rate, you need to increase the ventilation rate in order to match so that you have a consistent gradient for oxygen to diffuse into the bloodstream and carbon dioxide to diffuse out. So ventilation perfusion coupling is this matching of essentially your respiratory rate, although it's really the alveolar ventilation rate, with pulmonary blood perfusion or heart rate. We'll talk a little bit more in detail about that. So a steep partial pressure gradient for oxygen exists between the blood and the lungs. There is 21% oxygen in the atmospheric air. And then once we have all those factors that decrease it from 160, by the time it gets to the alveolus, it's about 104 millimeters of mercury. So a large partial pressure. We haven't got into internal respiration yet, but oxygen is going to be taken up by the tissues, leaving the bloodstream, so that when it comes back to the pulmonary capillaries to be reoxygenated, it is now down to about 40. So the partial pressure gradient at the level of the alveolus is 104 minus 40 for a pressure gradient of 64 millimeters of mercury. That is large, and that's good because oxygen does not dissolve very well in the plasma. Only 1.5% of oxygen is dissolved. So most of it is going to be carried on in the red blood cell and hemoglobin, and that will keep this at 40, and then the high concentration of oxygen in the atmosphere keeps this high at 104. This is the amount of time that a red blood cell could be, assuming that it's traveling along, it's not stuck in the capillary, it could be exposed to alveolar air for up to a second. At rest, the perfusion rate is relatively slow. Like our heart rate is relatively slow, and we're not perfusing at a high rate. 100%, and it's really not 100%, it's 98% because nothing is perfect, is reached in a quarter of the time, so in 0.25 seconds. And this means that there is a lot of reserve in capacity. So if we then start exercising and we start moving the blood a lot faster, we still have a lot of time to get a lot of capacity to get the red blood cell oxygenated. So the take home for external respiration with oxygen is oxygen exchange between the alveolus and the blood is driven by having a very steep partial pressure gradient. Equilibrium is reached very quickly, and so there is a large reserve to ensure adequate oxygenation even if blood flow increases 3 times. For carbon dioxide, the partial pressure gradient is much less. It's going to be about 40 in the alveolus, and a lot of this is due to the offloading of carbon dioxide from the venous blood, because in the atmosphere it's much less. But the partial pressure gradient between the blood and the alveolus is 5 millimeters of mercury. So this is very low. It's very small. But even though the gradient is not as steep, your blood can transport more carbon dioxide in the plasma, and that will assist in offloading carbon dioxide from the blood to the alveolus. So the offloading of carbon dioxide is greatly assisted by its solubility in plasma or water. This is a graph or figure that puts it all together, where we have inspired air. The partial pressure of oxygen is 160, partial pressure of CO2 is 0.3. At the level of the alveoli, due to mixing and offloading and onloading, the partial pressures are 104 for oxygen and 40 for carbon dioxide. So then it's going to travel through the system, and it drops a little bit here at 100 because of a decoupling and ventilation and perfusion and an alveoli not being available. So don't worry about that too much, but roughly the same levels that are at the alveoli travel through the systemic arteries. Then tissues, because of metabolism, they need to take up. Tissues are going to follow their concentration gradient. This is high oxygen down to low oxygen, high carbon dioxide down to lower carbon dioxide. And here it just gives you generalities because each tissue is going to vary depending on its metabolic needs and its location. Once it starts to hit those larger systemic veins, so your inferior vena cava, superior vena cava, the level of oxygen will be down to 40 millimeters and CO2 is up to 45. Then at the level for external respiration, these are the ones that you are comparing. The partial pressure gradient of oxygen is 104 versus the blood is at 40. So that large pressure gradient of 64 pushes oxygen into the blood. The reverse happens for carbon dioxide. The partial pressure gradient is 5 going in the direction of blood towards the alveoli. So the blood has the higher pressure, so it pushes CO2 into the alveoli. So always going from high pressure to low pressure. You might see boxes similar to this and say, where would I find this? So basically take this part out and maybe you'll see something that looks like this, or maybe you'll see something that looks like this. And you need to tell me where you would find it. Would you find these partial pressures in the alveoli? Would you find these partial pressures in the venous blood? Would you find them in the arterial blood? there will be a couple of choices. But this is a good graphic. So we talked about partial pressures and solubilities. Other things that can affect respiration exchange would be if the respiratory membrane were thicker, and then you would have a lot of distance to cover for diffusion, and it inhibits it exponentially. So you want to stay thin, but respiratory membranes tend to be thin. The surface area of alveoli is 40 times the surface of the skin, so tons of surface area. Normally, these two are not, under normal healthy individuals, these two are not going to be an inhibiting factor. However, certain pulmonary diseases reduce surface area, and then that can inhibit the rate of gas exchange. And so oxygen saturation will go down, and carbon dioxide still usually gets offloaded, but so it's more of an oxygen issue, which is why people with severe emphysema are on oxygen. Then that third factor was ventilation perfusion coupling. Ventilation and perfusion rates must be matched for optimal efficient gas exchange. Like I said, if you're doing slow breaths and you're exercising, you've got a decoupling right there. Our body is very good at controlling ventilation perfusion coupling. We tend to do a very good job. And this is because they're under local control. So local control overrides non-local control, and it's very quick, and it can go back and forth very rapidly. So it's very accurate. The alveolar PO2, so oxygen levels, are going to control the perfusion rate. So how fast it's going through is controlled by oxygen because it will affect arteriolar diameter. So it can cause constriction at the arterial level to decrease perfusion, or dilation at the arterial to increase perfusion. PCO2, so carbon dioxide, controls ventilation rate by changing the bronchiolar diameter. And when we get into acid-base balance, and you'll have a better understanding of how carbon dioxide is acidic and how we control acid-base, one of the major mechanisms is by altering ventilation rate. This relationship becomes more intuitive. But oxygen controls perfusion, carbon dioxide controls ventilation rate, and they get together and we get ventilation perfusion coupling. This shows if there's ventilation is less than perfusion, we get a mismatch. The pulmonary arteries serving will constrict. This will actually better oxygenate the system, and then we get a matching. This, you can read it. This diagram is not going to be on your exam. I much prefer these relationships as stated versus using a diagram for this one. Okay. So internal respiration, same concepts apply. Partial pressures and solubility. So, but now the diffusion gradients are reversed, okay? Because we're not going, we offloaded carbon dioxide and took up oxygen. At the tissue, we need to offload. So yeah, at the tissues, we need to offload oxygen and accept CO2. So if we're offloading oxygen, that blood level of blood partial pressure of O2 has to be higher than the tissues, and it always is. So tissue PO2 is always lower than arterial blood PO2. Arterial blood PO2 is at 100. Average tissue is 40, so oxygen moves from the blood to the tissues. Tissue PCO2, because we're metabolizing, we're producing CO2, will always be higher than that found in arterial blood. So CO2 moves from the tissues to the blood. So again, if you were given some values, you would need to know if, okay, so now we're talking internal respiration. If you were given a value of 100 millimeters of mercury, you would need to know if that's in the blood and that 40 is in the tissue PO2. So you'll be given some values and need to know if they would represent tissue PO2, arterial blood PO2, something like that. Moving on to how oxygen is transported in the blood. As I mentioned before, oxygen is not very soluble in water. So very little is actually dissolved in the plasma. 98.5% is attached to hemoglobin. If you remember, harken back to blood, hemoglobin is comprised of 4 polypeptide chains, so 4 globin chains. Each one has a heme group, and each heme group can bind an O2. So a fully saturated hemoglobin is hemoglobin plus 4 O2, so it's written as hemoglobin O8. Under normal resting conditions, hemoglobin is 98% saturated. And this, let's say, like once we get to the venous part, it's going to be about 75% saturated. Loading and unloading of oxygen are facilitated by a change in shape. As one oxygen binds, the hemoglobin changes shape, increasing its affinity for the next one. Okay, so here we have hemoglobin with no oxygen. Then we add 1, and the steepness of this graph is kind of how hard is it to add each hemoglobin. This first segment is the steepest. It's hardest to add this first one. Then it becomes less steep and less steep and less steep. So it's hardest to add the first one, still a little hard to add the second one. The third one is added very easily, and the fourth one really, really easily. When we unload, it's the same. It's very easy to offload the oxygen from the first hemoglobin. It's still easy, but a little bit more difficult to offload from 3 to going down to 2. It's going to become much more difficult to offload number 2 and number 1. By having this shape of a curve, it means that we're going to essentially take off oxygen from that 4th hemoglobin from all of them. And then the 3rd from like all in a given set of time. Obviously, you've got to account for that as well. But rather than stripping the oxygen off of one and then stripping the oxygen off of the other, we take a little bit from each one. So at rest, we move between, so when we pick up oxygen, we move between 3 and 4. When we get to the tissues, we move back to 3. With exercise, we go back to 2. And then at the level of the lungs, we'll go back up to 4. So we tend to play more in this part of the curve. And this curve's name is the oxygen hemoglobin dissociation curve. The physiology is that due to the shape of the globin proteins, as we increase the number of oxygen, it becomes easier to load oxygen as well as unload oxygen. Other factors can be temperature, pH, PCO2, and these will cause a shifting of that curve. And that's here. With an increase, like if we are exercising, the temperature at our muscles is going to be warmer. PCO2 is increased. Our metabolism has increased for producing more CO2. And then our pH is decreasing, which means our hydrogen ions are increasing. This is due to lactic acid and other byproducts of metabolism. And that is going to shift. It's called a right shift of the oxygen hemoglobin dissociation curve. And it makes the unloading of oxygen easier. Due to the changing in the shape of hemoglobin. Go through that. The influence of PO2 on hemoglobin saturation. Hemoglobin stays at about 98% saturation. So increasing the partial pressure of oxygen doesn't really do much to affect oxygen saturation. So my hemoglobin right now, hopefully, is about 98, 99% saturated. If I do deep breathing exercises right now, it's not going to change much. It might go up to 99. So we tend to keep hemoglobin pretty well saturated. In venous blood, the hemoglobin is still 75% saturated. We've got a huge reserve. And then locally with exercise, it can drop down to like 50, but that's not systemic. That's a very local interaction. We have a great oxygen reserve. Okay. Other factors. Okay, so this is what I was just talking about. The Bohr effect. This is increases in carbon dioxide, hydrogen ion, temperature, causes a right shift in hemoglobin oxygen dissociation curve. Any of these factors, increase in carbon dioxide, increase in hydrogen ions, increase in temperature, changes the shape of hemoglobin, makes it easier for oxygen to be offloaded. Our last, I think it's our last one, effect is going to be the Haldane effect. Okay. This allows oxygen to be unloaded where it's needed most. Carbon dioxide is transported in the blood in 3 forms. It can also bind to hemoglobin, and it's not competitive. So oxygen binds to the heme molecule, and carbon dioxide binds to a different location on that globin polypeptide. So it's not competitive. However, even though it's not competitive, it can affect the shape of hemoglobin. We'll talk about that. Carbon dioxide is much more soluble in water, so 7 to 10% will dissolve into the plasma. And then this is saying that this is not a catalyzed reaction. It's dependent on the amount of CO2. So the amount of CO2 that binds to hemoglobin is concentration partial pressure dependent. And this is to contrast with the next one, which is where the majority or how the majority of carbon dioxide is transported from the tissues to the alveoli for exchange. So about 70% is transported as bicarbonate ions. Oh, sorry. The primary mechanism for transport is as bicarbonate ions. This is a catalyzed reaction, and this occurs inside the red blood cells. So carbonic anhydrase is in red blood cells. And carbonic anhydrase is going to catalyze this reaction. With an increase in carbon dioxide, it pushes the reaction. So it's going to, you build it up here and it pushes the reaction this direction. So when carbon dioxide is released at the tissues and concentration increases, carbonic anhydrase, it rapidly forms carbonic acid. Then carbonic anhydrase is going to catalyze that reaction into hydrogen and bicarbonate. Bicarbonate then leaves the red blood cell and goes into the plasma. However, when bicarbonate leaves the red blood cell, the red blood cell can't sustain that ion imbalance. So chloride comes in. So when bicarbonate leaves the red blood cell, chloride ions move in to balance the red blood cell ionically. As the blood is then going to move through the pulmonary capillaries, bicarbonate comes back in, chloride leaves, and at the level, so this is the direction that we go at the level of the tissues. At the level of the lungs, it's reversed. So that carbon dioxide can then be excreted. So take-home message of carbon dioxide transport is that you do get a significant amount that dissolves in plasma and stays as carbon dioxide in plasma. It can also be transported on hemoglobin. It's not competitive, but its primary mechanism is traveling as bicarbonate ions, which it's converted to using the enzyme carbonic anhydrase in red blood cells. Bicarbonate ions travel in the plasma. Once we get back to the pulmonary circulation, bicarbonate goes back to the red blood cell so that it can be reconverted to carbon dioxide for excretion. The movement in and out of red blood cells is balanced by chloride ions. If bicarbonate leaves, chloride comes in. If bicarbonate comes back in, chloride leaves. So balanced by chloride. So this is showing transport and exchange of carbon dioxide and oxygen at the level of the tissues. So tissues are going to have the low oxygen pressure gradient. In the blood, it's much higher. That's going to facilitate oxygen moving from the red blood cell or the blood to the tissue. The carbon dioxide gradient is high at the level of the tissue. That is going to push carbon dioxide into the bloodstream. Carbon dioxide, some will dissolve in plasma, some will get carried as on the hemoglobin molecule, well, the red blood cell, the hemoglobin, the globin chain. But the majority of it will enter the red blood cell, be converted into bicarbonate and hydrogen ions. The bicarbonate will leave via the chloride shift. I would prefer the chloride switch, but I didn't name it. And then when we get to the level of the pulmonary capillaries, we get that switch again. Bicarbonate moves back into the red blood cells, switches with chloride, which moves out. That reversed reaction occurs. It's going to form carbonate and then be split by carbonic acid back into carbon dioxide so it can diffuse into the alveoli. So now we're on to our last, I believe it's our last effect, the Haldane effect. The amount of carbon dioxide being transported is also affected by oxygen. The lower the hemoglobin saturation, the more carbon dioxide can be carried in the blood.
Excuse me?
So,
Would you mind going back a few slides?
sure. To
Yeah, this one.
this one.
Yeah, I just want to get something. Thank you.
Sure. So this is the Haldane effect promotes carbon dioxide exchange at the tissues. The Bohr effect states that more oxygen is going to be released. So carbon dioxide is acidic. It pushes the dissociation curve to the right. More oxygen gets released. For the Haldane effect, as oxygen is released, it changes the form of hemoglobin so that it will more, it's more likely to accept carbon dioxide. Let's get back here. So text. Bohr effect aids oxygen offloading. And Haldane assists CO2 loading onto hemoglobin. And those are the globin chains. Of these that are on the board, these top four, we talked a lot about. You will see them in one shape or another. The most you would see Haldane is that it assists carbon dioxide loading onto hemoglobin or CO2 unloading from the tissues. Haldane's not one I'm going to focus on. You will definitely see multiple questions on the first four. Okay, so focus your studies on these. Don't worry about Haldane. 4 is enough, right? Oh, you know what? I didn't realize we've run out of time. Okay. Let's see, where am I? Let's see. Okay, so actually the last ones. Influence of carbon dioxide on blood pH. The carbonic acid bicarbonate buffer system helps blood resist changes into pH. We will study this much more in depth in acid base. Okay, so this will not be on your exam either. Changes in respiratory, and this again, acid base, we'll cover it under acid base. Read through the slides, not on the exam. This is I think it's a 5-minute video. If you want to watch it, it's pretty good. And you just need to download the PowerPoint and then it's embedded into the PowerPoint. Okay. And I realize we're at time. So that covers what I was going to cover today anyway. Just watch this on your own. And I will then see you on Wednesday. If you have any questions, email me and I will make sure that we cover. Wait, let's see. I'll see you on Monday, sorry. So this finishes Wednesday. Email me any questions if you want me to cover something on Monday's lecture before the exam. So I guess I should say I'm taking requests, for better or worse, because I have about 30 minutes of material to cover. So watch this on your own, and I will see you on Monday. And I'll see some of you in lab in a few minutes.